Welcome to Garrett ComSci. This is CS Principles, Unit 1, Lesson 6, Representing Text. So we'll be thinking about how do we represent text in the computer with the binary system. Let's start with a warm-up. Look at this list of values. We've got 1 space 1, 2 space 14, 7 space 4, 10 space 31. What could these mean? What could they represent? After a moment, you may notice that these are holidays. 1/1 is New Year's Day, January 1st. This is Valentine's Day. This is Independence Day. This is Halloween. So we've got these numbers that are representing something other than they are. So let's think about an activity that you could do in class, in person, with sticky notes and pens or pencils, where you represent a piece of text, like these text samples, using only numbers. Only numbers. How could you do this? Well, you might think maybe we use a number like 1 to mean A, and 2 to mean B, and so on. So, for the first challenge, with one partner putting their head down, the other partner tries to represent this piece of text on a sticky note using only numbers. What's the new complication with this? Well, here we have a space, and we did not account for that in our system. So what could we do to represent a space? If 1 is A, then that makes Z 26. Do we make space, that's a space, 27 maybe? Oops, my pen messed up. 27. Or we could make it 0. We could choose. Let's go with 27. The next example is this. Great. What are the new complications here? We have a capital letter G. They clearly want us to represent the capital letter G. And then we also have this exclamation point. So what are we going to do with that? Let's think about exclamation point. What do we do? We've got space at 27, so is exclamation point 28? And what about the capitals? You may think of all kinds of clever things like putting something else in front of it or something like that. Probably our best bet would just be to make a separate number for all the capitals. So what if we changed our system? This wouldn't be true anymore. To be 1 is lowercase a through 26 is lowercase z. And then maybe 27 is capital A, and so on. And then we move everything around so that we've got something for space, and we've got something for exclamation point, and we've got a separate code for capitals versus lowercase. And you could move these around as you saw fit. What's next? Okay, we have spaces, we have capitals, we have a question mark, so there's just another symbol to add to our list, and we've got now the digit 5. That's not really let's not think of that as the number 5, like 5 things. Let's just think of it as a character, that shape 5. So we'll want to add that to the list, and we'll probably want to add all the shapes 0 through 9 to our list somewhere. Who knows what they'll be? Could we say 100 and 100 is equal to the digit 0, and ... 105 is equal to the digit 5? Anyway, we could come up with whatever system that works, and we keep adjusting it as we think of more symbols until we have a complete system of all the stuff that you might use to make up some text. Not much different here. Digits, spaces, capitals and lowers, symbols like exclamation. So, is there anything we need to do to make all of this work and have all the stuff in it? Well, we'd want to come up with a system that has everything we'd want to possibly use in text. And we'd want to put a number with it. And of course, now we know that everything in the computer is really stored as binary. So we could give everything a number. Every symbol that we want to represent, like A, for example, gets a number, and then we store that number in binary. Binary. Oops. So here's that system in a very standardized way. This is called ASCII. We pronounce that ASCII. The American Standard Code for Information Interchange. It's existed for a long time, since the very beginning of modern computers. There are lots of codes that don't get used anymore in that system just because of the evolution of computers, but here are all the things that we might be interested in. Look, there's capital A. They've allowed capital A to mean to be the value 65. And there's 65 in binary. And it goes all the way through 90 for capital Z. And actually, at the early computers, everything was capital, and eventually they decided we need lower as well. Just kind of like we experienced with our little activity, we find more that we want to use. And so they added 97 is equal to lowercase a, and so on, down to Z. There's a little hint between capital A and lowercase a. The only difference is changing this bit right here. The third one from the left is changed to 1 to make it lowercase. And then they've listed these digits 0 through 9 here, starting at 48 for 0. And then here's space at 32. And then a bunch of symbols, bunch of symbols, bunch of symbols, more symbols. So there's a code for each one, and we use that number to represent each character, and then that character gets translated into binary. How many bits are they using to represent all of these? Let's look at the largest one that we see here. They're all the same number of bits, by the way, so that we know when one begins and one ends and the next one begins. So this is 1, 2, 3, 4, 5, 6, 7, 8. So each one is 8 bits, which is, of course, 1 byte per character. And so to make some text, we put 8 bits for one character right next to another 8 bits for another character, and we just look at each multiple of 8 to see what character they are. All right, so we solved the problem of representing text, which is not numeric, as a number that is then stored as binary. So we're able to represent more than just numeric information in binary. We can represent all kinds of real-world information with patterns of zeros and ones, binary numbers. So This is our first glance at the concept of abstraction, which is one of the big ideas of computer science principles. Text is a piece of information that we think about on a high level, like when we type a text message to someone, how's it going? That's really all we're thinking about when we type that. But really, it's being stored using this system called ASCII that assigns a number, a decimal number, to each of the symbols that we use. So here are all those decimal numbers for each of the characters used. See, there's the 32 for the space in this message. But really, ASCII is not what's stored in the computer, is it? The 8-bit binary equivalent of each of these numbers is stored in the computer. That's not really what it looks like. We could find out if we wanted to by storing each number side by side. So, the concept of abstraction is that we can think of information on multiple levels. And we can just think of it on the highest level that we work with, like text, and know that there are layers underneath that are also true. So really it's using the ASCII system, but really it's representing all the ASCII numbers in binary. But yet text is an abstraction because we can just think of that level, and that's how we use it. So text is an abstraction because we are using it at a high level, thinking about it at a high level, and hiding away different levels of detail under the surface. What's another example of an abstraction from your everyday life? So something where we don't completely understand what's going on beneath the surface, but we can still use it with confidence. Maybe you're not a driver yet, but you know what a car looks like. Imagine you're in the driver's seat of a car and you've got a steering wheel and a couple of pedals and maybe some buttons. You don't necessarily know what all is happening to make the car go when you hit the gas pedal. There's a whole lot happening under the hood to make the car move forward when you hit the gas pedal. But you just think of that highest level, that most surfaced level, which is the buttons and the pedals and the wheel. And all the detail is hidden away from you so that you can just focus on using that surface level. That's abstraction. This has been lesson 1.6. Go ahead and hit subscribe if you haven't already, and go on and continue to lesson 1.7. Thank you for watching. Bye.